Okay, problem number 3 is to repeat homework problem number 1 for a line length of 175 kilometers. So if we have a line that's between 80 kilometer and 240 kilometer, we use the medium line. And the medium line model is called the pi model, and it looks like this. We have a capacitor at the input end. Take half the lump capacitance, we put it there. Then we've got a series resistor, series inductor. Then we have another shunt capacitor with a value of C/2. And that's the output end of the line right there. So you can see it's the same model. We've just put these shunt capacitors at the input and the output end. So this is your receiving end voltage right here. This is your receiving end current. A lot of times we'll label this current the capacitive current receiving end, and similarly we'll label that current the capacitive current at the sending end. And then we've got the current in the line I, and then we've got the current at the sending end and the voltage at the sending end. So the solution for this, the governing equations that we typically use, are that Vs is equal to Vr plus I times R plus J omega L, where I is equal to ICR plus IR. So that gives us the sending end voltage. And if we need to calculate the sending end current, it's I plus ICS. Now, this problem didn't ask that, but I just thought I would point it out that there is a KCL action happening at that node right there. So what we need to do to solve this problem is figure out what the sending end voltage or the receiving end voltage is from the problem statement. We calculated that in problem number 1. It's not going to change because the load didn't change here, so it's still going to be 66.4 angle 0 degrees kV. And then the receiving end current we also calculated in problem number 1 from the load information. It came from the power and the power factor. We found out that that's 86.96 angle negative 30 degrees amps. So those are from the previous problem. You would have to solve those, of course, if you hadn't already. So now what we need to do is we need to figure out what that line current I is, and that's this formula right here. So we need to calculate ICR. We didn't have that. So we can see that the current flow through this capacitor is the voltage across it, which is VR, divided by its series reactance. So that's the formula we're going to use for that. So ICR is going to be equal to the voltage across the capacitor, which in this case was just the receiving end voltage, and it will be divided by XCR. So that was 66.4 angle 0 degrees kV, and then XCR is 1 divided by J times 377, which is just 2 pi f for a 60 hertz system. The capacitance was 7.387 nanofarads, but we need to divide that by 2 for this model. Half of it goes at the load and half of it goes at the source. Okay. So that gives us C. We now need to multiply by the line length, which was 175. Remember, this is farads per kilometer, and that's kilometers right there. So those cancel and give us farads in the numerator, which is the unit we need to be able to calculate ohms for our shunt capacitor there. So if you do that correctly, you should get a receiving end capacitive current of 16.1799 at angle 90 degrees amps. And so the total transmission line current is going to be the load current, 86.96 angle negative 30 degrees amps, plus this 16.1799 angle 90 degrees amps. Add those together and you're going to get 80.11 angle negative 19.93 degrees amps flowing in the transmission line. We then just use our model to extrapolate the Ohm's law and KVL. It's going to be 66.4 angle 0 degrees kilovolts. That's the load end voltage plus the voltage drop across the line, which is the product of the series current and the series impedance. The problem number 1 told us that the resistance was 0.00893 ohms per kilometer plus J 377 times 1.554 millihenries. We need to multiply that by line length in kilometers again. And so I got a source voltage of 69.7 kV at an angle of 6.3 degrees, which if we want it on a line-to-line basis, multiply that by root 3, which is 120.8.